Well, good morning. Did you pick up the diffraction grating? We're going to look at linear spectra right here. I've got hydrogen tube, helium. Actually, what's the difference? Diatomic gas, monatomic gas. So here you're going to look at the molecular spectrum, and this is an atomic spectrum. And for that, you need a diffraction grating. We know it splits the light, and we know it does it differently for different wavelengths. Some kind of echo. Do you hear me fine? How was the sound? Okay, thank you. So, and we know that the central maximum, you should pick up, oops, third one. That's why I keep this slide on. The central maximum will be white because red, blue, green, they all go through directly to the central maximum. That don't mix, don't separate, mix. But so looking at the middle direction doesn't give anything interesting. So we'll have to look aside to find the first maximum, and I'm going to stack them up. Which it's easier to see. And I'm gonna kill the light. And at the top, of course, you're not gonna see anything like this. You're gonna look to the left or to the right. And if you look at about, 25, 30 degrees, you start seeing lines, blue, or violet, green, yellow, red, they to the right. And if you look higher, you can see a rainbow, continuous spectrum. Of course, because the filament produces light of all color. But if you look lower, well, for the helium, you don't see many lines. But for hydrogen, yeah, you can. I can see at least 1, 2, 3, 4, 5, 6 lines at the bottom, at the lower spectrum. And you can see they're different. So a spectrum for each element is like a fingerprint, a unique spectrum. So that's why we can look at anything and find what elements are there. For example, that is how helium was originally discovered. Someone just looked at the sun and they found lines which didn't exist before. And only after the helium was found on the Earth. And astronomers have been looking around for, well, 100 years. So by now we know, so far in the universe there is nothing else but same periodic table, nothing so far. Exactly same set of elements everywhere. And well, the only one real mystery remains is Where are the aliens? They should be somewhere. Why are they hiding? Are they scared of us? Well, now a question. Helium, the second element in the periodic table. Helium-4 specifically is a stable isotope. Has 2 protons, 2 neutrons in the nucleus, and 2 electrons orbiting. So what can we do? We can weigh one atom get rid of electrons. That will give us the nuclear mass, the mass of a nucleus. And we can weigh each proton, each neutron individually. Well, first of all, of course, it's about bonding energy. And again, as an illustration of what it might be in general, as long as at least 2 objects attract each other, there is always binding energy. We just didn't call it that way. Even if we just had just any negative charge and any positive charge, they would attract each other. So if we want to move a charge away, well, let's say this is fixed, and we use our hand to apply a force to move it away, the work done by us, by applied force, will be positive. Because, well, the easiest way just, displacement or velocity points to the right, and work equals magnitude of force, magnitude of displacement, times cosine of the angle. In this situation, angle is 0. So this is the amount of work which has to be done to break this system apart. And again, that was actually lecture number 4. We talked about potential energy 5 weeks ago. So potential energy for 2 opposite charges will be equal to, well, charge number 1, which is positive, times charge number 2, which is negative, divided by the distance. That's initial. And it will be a negative number because one charge is positive, second charge is negative. It has to be negative product. But the final potential energy will be equal to 0 when these 2 charges are infinitely far away. The distance is infinitely large. That's it. So how would we calculate the work done? Again, lecture 4. By what? The work done by electric field. By electric field should be equal to initial minus final potential energy. That's a definition of potential energy. But the work done by a hand, by an applied force, should be equal to opposite to that. So will be final minus initial. And again, it confirms that 0 minus a negative number gives positive amount of work. That is basically binding energy. The amount of work which has to be done to take it apart, that's the binding energy. And in this situation, we know that because we have to do work against the strong nuclear force. So initially, we have certain amount of energy stored in the nucleus. We have to do some positive work to get finally those 4 nucleons separated. So divided by c squared, Einstein's equation, which relates mass and energy. So this will be the mass of the nucleus, and we have to add a certain number to it. That's not a specific mass, this is just a number associated with the binding energy, some positive number. And that should give the mass of individual nucleons, so 2 of the protons, neutrons. So because this is a positive number related to a positive amount of work done, well, that again tells us that in terms of masses, a nucleus has less kilograms or grams or atomic mass units than all those particles individually. And the mass difference has a name, mass defect, or outdated mass deficit. So how would we calculate? Yeah, a specific example. How would we calculate? You can't answer this question yet because you don't know what I am asking. So first we have to wait. So we need to calculate the binding energy starting from mass defect. And well, have to subtract 2 numbers. One number represents the individual masses of protons and neutrons. So 2 times for the proton 1.007276 plus for neutrons 2 neutrons times 0.08664. Now we need to subtract the mass associated to the helium. Now you can tell me, what do you think? Is it a correct calculation? Is it a wrong calculation? Could it be both? Could it be automatically correct and wrong? I'm giving you a hint. Please start selecting your answer. What did you select?
Looks wrong.
How does it look wrong? I see all the letters delta m equals 2. I understand everything. What's wrong? We are looking for the binding energy. If we calculate the mass defect, which is this, all we have to do, we just multiply by a coefficient. If we calculate mass defect in kilograms, the coefficient is speed of the light squared. If we calculate this number in atomic mass unit, the coefficient is 931.5 mega electron volts. So, yes.
You're using atomic mass, not kilograms.
Why? Yes, but why do you think I'm using atomic mass, not nuclear mass? What's the reason? I know, that's wrong. I'm using the wrong mass, yeah. The question is why? So it is wrong. Why? Because that's a typical mistake, and I want to show you a typical mistake. But it's an easy fix. We have to remember the difference between the atomic mass and the mass of a nucleus. Atomic mass includes the electron masses. So it's an easy fix. If you want to calculate the mass defect, we start from the same individual masses of a proton and two more masses of a neutron. And now we have to subtract what? Well, how do we get the nuclear mass from atomic mass? That's the atomic mass. And what do we need to do to that to make it the mass of a nucleus? Exactly how many electrons? 2. So we have to subtract 2 electron masses. 0.0054858. That's going to do it. And then we can multiply this number by this coefficient. So the binding energy will be equal to, whatever it is, 2 times 1.007276 plus 2 times 1.008664 minus. Now, too many parentheses. So first of all, for electron mass, a minus and a minus, what does it make it? A plus. 2 electrons, 5, 4, 8, 5, 8. And now, finally, we're subtracting the atomic mass. And now times 931.5. Bless you. 931.5. Again, mega electron volts. Mega means 10 to the 6 millions. That's it. Of course, we can make a generalization. That's a specific example, but in general, what would we have to do? Well, the mass defect should be equal to what? Again, well, just mass defect. How many protons should be used in general? Z protons. And each proton has a specific mass, the mass of the proton. How many neutrons does it have? Well, if we know the atomic mass number, we have to subtract the number of protons. That will be the number of neutrons, and we have to multiply by the mass of a single neutron. Now we have to subtract the mass of a nucleus, but it is equal to the atomic mass minus how many electron masses should we subtract? Z, the same number as the number of protons. That's it. So basically, we always can use atomic mass. We just need to do this calculation, which includes protons, neutrons, and electrons again. Minus and minus makes it plus electrons. So this is a general calculation we can always use to calculate the mass defect and multiply by 931.5 to get the binding energy. So we have it here. So this is a calculation in joules. in that situation, everything is in kilograms, and this is speed of light in meters per second. But don't do that. Why? It's much more complicated. Much more easier would be using atomic mass units and just multiply by 931.5. Automatically gives you mega electron volts. What do we have here? Yeah. So the number of protons from the periodic table, the number of neutrons, and we know the number of electrons is equal to the number of protons. Chemistry. Oops, what did I do? That's what I want to do. One more example just to practice. Carbon. So, please take a minute or 2 minutes and calculate mass defect. That's what we need, because then we can just multiply by 931.5, that's it. So carbon 12 at the stable isotope, how many protons does it have? You should look it up. Hydrogen, helium, lithium, beryllium, boron, carbon. 6 numbers. 6. So how many protons? And how many neutrons? And how many electrons? And the only number which we need to kind of figure out is what is the atomic mass of carbon 12? And I can tell you, we have answered this question yesterday on a slide 27. And maybe I'm lying, but you don't know what's on the slide 27 anyway. So. But I know it's somewhere there. Atomic mass of carbon 12. So if we want to calculate binding energy, we know that the order of multiplication doesn't matter, so we can start from a coefficient 931.5 times 6 times actually it's going to be 6 and 6 and 6, correct? So 6 will be a common factor. 6 protons, 6 neutrons, 6 electrons. So what I want to do, I want to just add them up all together. 1.008664 plus 1.007276 plus 0.00548858 equals 2.016488858 atomic mass units. Yeah, every year I write worse and worse, something happening in my brain, or in my arm, or in my heart. So 6488858. And now we need to subtract the atomic mass of carbon 12. Please tell me the number. 12, because according to a definition, one atomic mass unit is 1/12 of that. That's it. So, first of all, immediately can see a positive number. 6 times 2 is 12, but there is something else, and we're subtracting 12. So there is binding energy. And what is going to be? Why did I erase it? I just had to 2.016488858 times 6 minus 12 times 931.5 equals 92.16 mega electron volts. Now, there is another very important physical quantity related to all elements is binding energy per nucleon. How many nucleons does it have? A. The number of nucleons is equal to the number of protons and neutrons together. So to calculate the binding energy per nucleon, we just have to calculate this ratio, 92.16 over how many? 12 divided by 12, about 7.7 mega electron volts per nucleon. There is a graph, of course, for all known elements. This energy per nucleon has been calculated. We can see where it peaks. And so that's calculation. That's the binding energy per nucleon. And that's the graph. We can look at this graph. We can see that, for example, uranium and carbon have very close binding energy per nucleon, but carbon-12 is stable, never splits, never decays. And uranium has no stable isotopes at all. Any isotope of uranium decays always, some are faster, some are slower, but they all decay. Why? Well, we know why, because it's all about balance between strong force and repulsive electric force. For a small nucleus, the strong force wins over, but if electric force decreases inversely distance squared, the strong force increases decreases much faster. So these nucleons which far apart, they cannot provide strong attraction anymore, and repulsion wins over, and eventually the electrostatic force breaks it apart. And that's what we call a decay. And well, if you go to this link and you look at the chart, you can look at different elements. Some elements below a certain number have stable isotopes, but above a certain number, stable isotopes just don't exist anymore. For those, for large nuclei, strong force is not strong anymore to keep them together. Question. Oops. Come on. Well, you can see it. So, question. I have a die, and I'm going to roll it. What's going to happen? This is a situation where I expect everybody entering exactly same number. 100% correct answers. I will roll it. What did you press? What did you choose? Did you choose your answer? What is that? Are you saying or are you asking? I'll check right now your answer. Interesting. Well, I think the distribution represents the wish. I wish it would be 1. I wish it would be 6. What is going to be? Five. Sorry, you lost. I won. What's going to be now? 4. It's unpredictable. Some of them, of course, will be there, but it's unpredictable. And that's what radioactivity is about. In classical physics, when we throw a ball, we can predict exactly when and where it's going to be if we know initial conditions, speed, forces acting on it. In quantum world, that's impossible. So let's say I have uranium-238 nucleus. I place it, well, 238. It's not a good example. It would take millions of years before it would decay. So 235, it decays much quicker. So I place it and I look at it. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4. Something happened. It splits, it decays. All right, I write it down. First atom, 7 seconds. I take another atom, place it, wait until it splits. I write it down. 22 seconds. Same atom, different time. So what do? I keep doing the same. 15 seconds, maybe 17 again, maybe 22 again, maybe 17.5, etc., etc. I have to do it a lot, many times, but after a while, I can see the average. So the average values only describe large numbers of events. It's practically impossible to make a prediction what will happen to a specific atom. But we can predict what will happen to many of those. We know that if we have many of radioactive atoms and we wait, eventually some split, another one, another one, another one. So if we use a large number of atoms, the number of decays per second depends on the amount of material we have. So this word activity in physics has two different meanings. First, radioactivity, we call a phenomenon when they split eventually. But also, there is a specific physical variable, physical quantity we call activity as well. And that is if we have a specific amount, of radioactive material, how many decays happening every second? That's what it is. That's what activity is by definition. And of course, if you have only few elements, well, that means activity is low. If we have many, that means activity is high. So activity, the number of decays per second, directly proportional to the amount of radioactive matter, or radioactive material. And first of all, this letter R, that's a standard symbol for activity. The unit of activity in international system of units is a becquerel, BQ. So it's 1 over a second because a number has no unit. Now, what it should be equal to? Well, the magnitude of it should be proportional to the number of elements, radioactive elements. If we have many, activity is higher. And the coefficient, of course, depends on, there's a specific coefficient. It depends on the material. This coefficient looks like wavelength because same letter, but it's not. Just historically, people use this coefficient, this letter lambda for the coefficient, and we call it decay constant. A decay constant is a coefficient which relates the instantaneous number of radioactive elements and the activity of this particular sample. A huge number, high activity; small number, low activity. What do we do now? Number of decays per second, that's what we call rate. Rate of change of position, velocity, rate of change, velocity, acceleration. For any rate, we always have change in something over time. That's what rate mathematically means. The only problem is the number is a positive number. Yeah. We count the number of elements, one nucleus, second, third, is positive. But because it decreases in time, of course, if we start from a certain instant, we have a certain initial number of these elements, but they decay. So if we wait a little longer, less remains, and then less and less and less, which means delta n, final minus initial, should be negative. Should be negative. Delta n is negative. How do we fix it? Well, we have to write a minus, exactly like we did for Faraday's law, for example. So this is an official definition. Well, this is an official definition of activity, and this is an official mathematical equation for activity. And if we combine these together, what we have is an equation for the number of radioactive elements, how this number changes in time. Well, same equations. The problem is we don't know how to solve this equation. It is an equation. So technically, again, if we sketch a graph, it should look like this. The number of radioactive elements decreases in time from initial, well, eventually to 0. And what is delta n? What is rate of change? That is also called slope. And what is a slope? A slope is a tangent of a line. It is negative, as we can see, as it's supposed to be. But this slope here should be equal to this number there times this constant. Slope equals this. Well, we don't know how to solve it, but it's been done for us, of course. And the answer is this graph describes the exponentially fast decrease. This is the answer for this equation. What does this letter mean? Anybody? Cannot hear you. Yep. This is just a fixed number, 2.7. 2.71, just a fixed number. That's a second important number which has a specific letter assigned to it. We know pi, yeah, 3.1415 96. And now there's another number. What is the definition of pi? Anybody? It's a ratio of circumference over diameter. That's it. What is the definition of E? Well, in mathematics, there is such things like a logarithm. That's what it is. We don't need to know that. We don't care. For us, it is just a number which is relatively close to 3, like pi, relatively close to 3. So this graph tells us how to calculate how many radioactive elements remain after certain period of time if we start from the initial number and the material is described by this specific decay constant. So this is now, this is at t equals 0, this is now at t equals t. That's it. So the variable inverse to the decay constant has a unit of time, seconds. This variable has a name, lifetime. What does it mean? If we use this equation, actually, now I want to add it. If we use this equation, and a definition of lifetime, the same equation can be written in terms of this ratio, time now over lifetime, which tells us that this instantaneous value will be equal to the initial times about, closely, 3 and this. Now, what does a negative exponent says? That actually says this. We have to divide by 3 to this ratio. If we wait exactly one lifetime, how many radioactive elements will remain in one lifetime? It will remain about a third of the initial, about, close. Yeah. We replaced E, 2.71, with 3. So every lifetime period, the number of radioactive elements decreases in about 3 times than before. That's what it is. Basically, nothing else. So this is the equation, the meaning of lifetime, and the question. The question is about 2 different elements. For the first element, this black line represents how fast the number of radioactive elements decreases with time. And now we need to figure out which of these lines, the red or the blue, represents an element with a larger decay constant. And you should choose. If you think the red, choose 1. If you think the blue, choose 2. Decay constant, of course, is not very intuitive, but lifetime is more intuitive. If decay constant is larger, that means lifetime is short. Okay? Which means large decay constant means the number of elements should decrease faster it takes less time to get from initial to the third of that. Less time. Large decay constant means faster decrease. Small decay constant means this is a large period. It takes longer time to drop to 1/3 of the initial. So, what is the answer? What do you think? What do you think? Red or blue? Which graph, red or blue, shows faster decay? Red. Where is 1/3? 1/3 is 1/3. 1/3 is about here. It takes less time for the red, T life red, to get to 1/3 than to all others. So for the red graph, we have the element with the largest decay constant. That's how it works. So again, well, actually, I just said it. We don't need this. So the answer, faster drop. This is the summary. Plus, we need to take a note of a difference between two words: radioactive element and the radioactive sample. Element samples. So if we start from the same amount of radioactive elements, 66666666666, we wait one lifetime. In one lifetime, we should observe left about 1/3 of initial. So 1, 2, 3, 4, 5, 6. I should have counted before. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. So 1/3 means all these are something else, but only third left. But so physically, they all belong to the same physical object, to the same sample. So if I ask, what happened to the mass of this radioactive element? The mass of the radioactive element decreased because the number of radioactive elements decreased. But if I ask you, what happened to the mass of the whole sample? It's practically the same. They all remain inside the same containers, the same physical object. So when we read a problem about what's happening to the mass, the answer depends on the mass of what. If it's about the mass of radioactive elements, it decreases with the number of elements. Yeah? The number of elements decreases. How do we calculate the mass? Well, the chemistry says just take the number of atoms, multiply by atomic mass. So this mass decreases, but because they all remain inside, practically all, 99.99%, only those who are close to the surface might emit something. So the mass of the sample remains the same. Well, so there has to be a better way, and of course it does exist. This applet demonstrates the radioactive decay for, I think it's 1,000 elements. So we can see every red dot represents a specific nucleus, and they decay at different times, but eventually there must be a specific time when exactly a half decays and exactly a half remains. It has to be. It has to happen somewhere. We're so close to that. Okay. So now, if we count how many decayed and how many remain, 50% of initial amount decayed, which means 50% of the initial amount remain inside. And of course, it takes a specific amount of time. This time has a name, a half-life. So now we have two different times, lifetime and half-life. Again, the lifetime is a period we need to wait until about a third remains. Half-life is a period of time we need to wait until half remains. That's it. How can we write it mathematically? Well, first of all, a definition of half-life. That's a standard symbol, which is not lifetime. A definition is if we start from a certain initial number and we wait exactly one half-life, use your imagination. On average, for a large sample, we should reach left exactly a half of the initial. That's what it is. How do we write it mathematically? Well, n initial over 2 should be equal to the initial. Well, over 2 to the first, or times 2 to the negative first, or times 2 to the negative, and this is the ratio between this instant and a half-life. So if we wait a certain period of time, we can count how many half-lives we can fit in it. Normally people use just the letter n for that. Technically it doesn't have to be a whole number, but for any simple problem it's 1 or 2 or 3 or 4. And now what we do? Well, we say that if we wait so many half-lives, we will be left with this number of radioactive elements undecayed, not decayed, remained. The initial number divided by this number of half-lives, because every time it decreases by a coefficient of 2. If we wait one more half-life, so it drops to what? By definition, it drops to a half of the initial for this period. So here it will be a half of the initial, which is this. If we wait one more half-life, here the number will be a half of the initial for that period, 2 cubed, etc., etc. And that is how we get this equation. Both equations have the same name, the law of radioactive decay, but one is more complicated. This is easier. So this is the graph, the same graph, we just read it differently. Instead of using lifetime, we use half-life. In one half-life, we have left with a half of the initial. This is a half of the initial, which is a quarter of the initial to initial. We should say previous. Yeah? 1/8, etc., etc. So all we need to do is just count powers of 2. The summary and some mathematics for curious people. Of course, mathematically, there should be no difference. In mathematics, of course, we can go from one base to another base, from E to 2, from 2 to E, which means those two numbers, half-life and lifetime are related. This is how. Of course, it's a natural logarithm. And another summary. And the equation sheet actually has the copy of this part, so just to keep list of powers of 2. Another summary, difference between lifetime and half-life with initial definition of activity. Some examples of different half-lives. Of course, they've been measured for all important materials, and you can see it spans from fractions of a second to billions of years. It depends. How can we measure? If it's a billion, we cannot wait billions of years. We would die. But we don't have to. Instead, we can use a huge number of these elements and just count how many left in an hour. That's it. And we're done with the theory. What do we do now? Short memory test. Just in case, you need to check how your calculator calculates logarithms for maybe 1 or 2 homework problems. You may need to do that. I don't remember now. Now, so here, it's basically about physical meaning. Of course, there is an equation 2 slides before which relates those two, but you don't remember that equation. So what you have to do is physics. And physics is in the graph, is in a definition. We start from a certain number. We can call it 100%. It doesn't really matter. And eventually, we get left a half of that. What is a half of 100? 50%. Or eventually, we get left with a third of that. What is a third of 100? About 33%. So this happens, so that's the graph. This happens at this instant, and this happens at this instant. So this is a capital T, this is capital T. All we need to do is choose the subscript, right? That's time. And now the word half gives it away. Which is a half-life out of these two? The left or the right? What do you think? Half-life. This one or this one? Say any. No. Right is not right. A half means divided by 2. To which point should we get from 100 if we divide it by 2? 100 over 2, 50. This is a half-life, which automatically means this should be lifetime. And lifetime is longer. And the equation tells us we don't have to use it, but it's on the equation sheet. And if you calculate the natural logarithm of 2, what does it give you? The natural logarithm of 2 is equal to about 0.7. Yeah, so we take a number and multiply it by fraction. Well, okay, so the summary. Now, the question, I'm going to give you a minute or two to try to figure it out. So the word now normally means the initial instant, the time when we start the stopwatch. Starting from this time, the number of radioactive elements decreases. In this situation, it decreases from 128. So we have managed to have 128 nuclei of the same element. Where is it? Here. T equals 0. And we are waiting and counting. And well, this is actually what we can write down. Left remains in, so in the sample 64 in 1 hour. So first of all, the equation, the easy way to write the law of radioactive decay immediately tells us that we've been waiting exactly one half-life, which means 1 hour is a half-life for this material. So in 1 hour, we got left. If we wait 1 more hour, what's going to happen? 64 over 2. We got left with 32. If we wait 1 more hour, we're left only with 16 of the original. 1 more hour, 1 more hour, 1 more hour, 1 more hour. So if we wait 1, 2, 3, 4, 5, 6, 7 hours, we will be left with only 1 of the original radioactive atoms. We had 128, and now we only have 1. But it's still there, and it will eventually decay. So we have to wait on average 1 more half-life. Well, about an hour more until nothing is left. So 8 hours. The question is, can we find the answer by mathematical equation? Yes, we can, of course. But again, counting half-lives normally is much easier. So let's do it mathematically just to make sure. First of all, nothing is left. What does word nothing mean mathematically? 0. So our first intention to write an equation, can we solve this equation? Well, we can try. 2 to the nth will be equal to 128 divided by 0. What does it tell you? 128 divided by 0. You should try at least once. What do we see? Error, because we cannot divide by 0. So this equation cannot be used for zeros. So what do we have to do? Well, we have to set it to the smallest possible value. 1 equals 128 divided by 2 to the nth. Hence, 2 to the nth equals 128, which is 2 to the 7th. So n must be equal to 7. But what does it mean? It means if we start from 128, we have to wait 7 half-lives until we get only one left. Well, and then if this has to decay, we have to wait one more. So of course we can use equations. We just have to use some actual number for the final number of elements. So again, from here to here, 7 half-lives plus one more. Well, this is again the standard strategy. I just did it. So next example. Don't answer this question. Let's just do it. Let's just do it because I'm running out of time. Again, now, what does it now mean? At t equals 0. We start from 1024 radioactive elements, and we again wait 1 hour. Took a nap, woke up, and we know that 64 of original number left. So, what can we do? Well, this is 1 hour. So what could we do? We could set 64 should be equal to the initial number. Well, again, the equation says where this number n represents the number of half-lives fit in that particular time interval. We're counting half-lives. 64 should be equal to 10. 24 divided by 2 to the number of half-lives. How do we solve it? Well, 64 equals 2 to the 6th. I don't like fractions. I don't know about you, but I don't like, so I always cross-multiply. And that should be equal to 2 to the 10th. I'm just using that table. It saves time. Now what can we do? Well, mathematics says if we're multiplying two powers with the same base, we can combine them together. And that's going to be 6 plus n. And that should be equal to this. But that means because the base is the same, 6 plus n should be equal to 10. So n should be equal to 4, which means we have to wait 4 half-lives. And the same answer comes automatically from just counting. We have to wait 1 half-life to get from 124 to a half of that. Then we have to wait 1 more half-life to get from 512 to a half of that. Then we have to wait 1 more half-life to get from 256 to a half of that, and 1 more. So 1 hour is equal to 4 half-lives, which means half-life equals a quarter of that. A half-life of this material will be equal to 1 hour over 15 minutes. Again, let's don't do that. This is a slightly different situation, but I want to cover it. What is the difference between the previous problem and this one? One word, but it's very important. How many left? 64. How many will decay? So we need to remember, what does this letter N mean? It means left, remains. So if we start from this and we go down to this, How do we calculate how many decayed? The difference says how many disappeared. And that's what it is here. How many decays? This many. But now, of course, everything is clear. Now we can find how many remain. This will be equal to 1024 minus 1008, 16. And now we can write an equation. 16 equals 1024, 2 to the nth. Or we can count 1, 2, 3, 4, 5, 6. 6 half-lives. So annoying, I know. I'm here. Well, oh, it's getting louder. Well, I don't know what happened. Well, actually, I do. But it's Wednesday. What do we do every Wednesday? Oh, maybe not every Wednesday. We do evaluation. And you've done it before. So you know nowadays it's done online. So you should check your email. You should receive an email with the same link, or you can just copy the link. If you don't have an email, please let me know. I can send it. But I'm done for today. Tomorrow we have the last lecture, and it's going to be relatively short as well. So maybe last 20, 25 minutes we can spend for questions and answers if you prepare those questions. And I'm going to go to do my office hours very soon. And or what do I have to do? Just take this off, take this down. So please, this is important. There is no www. Because if you try, the link will not work. But if you just enter this address, it should lead you to the website. Officially, I'm already not here. You don't see me. Or you see somebody else, I don't know, it's not me. Someone else is drinking coffee. And then, of course, you don't have to wait until 10:30. Yeah. You're free to go. And next, what do I do? I take this, I take this, I take this. Don't forget to sign in, please. I will collect the sign-in sheets later in 10 minutes.
Defect a lot today?